We now move from digital intelligence to physical intelligence. For years, AI has transformed how we search, write, analyze, predict, and automate information. But the next frontier is far more complex, bringing intelligence into the physical world. Robotics is where AI must understand not only language and data, but space, movement, uncertainty, objects, environments, and real-world consequences. This is the frontier of physical AI, where machines begin to perceive, reason, and act in the world around us. The challenge is not only to build smarter robots, it is to build systems that can operate safely, adaptively, and reliably in the complexity of real life. Please welcome Nikolay Nikolov, researcher at INSAIT, with his keynote, Physical AI, Solving the Next Frontier in Robotics.
Hello, everyone. I'm Nikolay Nikolov. I'm currently a researcher at INSAIT, which is an institute here in Sofia, affiliated with Sofia University and also ETH Zurich, which is a Swiss university. And today I'm going to talk about physical AI, and I'm going to focus on what's the next frontier in robotics. But to understand this, we need to go through a brief history. So I will also go through a brief history, and I have structured my presentation as a series of somewhat contrarian views about how the future of robotics is going to develop. So brace with me. I'm going to start with the most mild one in the beginning, which is that the LLMs that we see today, they only solved language, but they didn't solve intelligence. And to illustrate my point better, if we walk through history, at some point, history of life, at some point, amoebas and the most simple organisms formed. Then it took us around 3.7 billion years to reach to apes, to evolve there. Then another 20 million years to evolve to humans, another 5 million years to develop reasoning and language, and then another 150K years to evolve to where we are today now. And if I compress this timeline in 24 hours, so we are going to see that it took us only 60 seconds to develop these language and reasoning capabilities. However, it took us 20 hours to develop the hardware and the physical intelligence that we need to operate in this real world. So I'm arguing that physical intelligence is much more difficult to develop compared to reasoning and language. So let's talk a bit more about robotics, and let me show you what are the difficulties there. And going to my next contrarian view, it's that generalist robotics models will wipe out the vertical solutions or the vertically integrated models. Let me show you what I mean by that. So hand-engineered robotics was how we were doing robotics since, before AI, before AI became more prevalent and started working. And what's the problem with that? First of all, it's fragile. You need to program for a specific environment over months or years, and your robot is going to work only in that environment and only for that task. Then there's zero common sense. If the model sees something that hasn't been hard-coded into it, if it sees an edge case, it's not able to adapt. It doesn't have this ability of humans to adapt to adapt to unseen situations. And as I said, it's again environment dependent. So you put this robot in a different environment, it's no longer working. This is a video from the famous DARPA challenge. It's from 10 years ago. These are the best solutions that people managed to develop back then. These are hand-engineered robotics. Like, it cannot even walk in a stable way. They are struggling a lot. Okay, can we push this further now? And yes, the answer is yes. Like, this is a video from a famous company, Boston Dynamics. They managed to push this further. So, like, as you can see, the robots here are a lot more stable. They can now perform a lot more complex, in a way, skills. But again, the problem is that this is hand-engineered, and this is like for this specific environment. This kind of solution takes around 12 months at least to develop, and requires a team of multiple experts to build something like this. And I'm arguing that that generalist robotics models are going to be able to solve these problems. And these are videos. They're extremely fresh. They're like 1 month old, some of them, demonstrating what we have been able to achieve with these generalist robotics models, which can adapt to different environments and perform skills that they haven't seen before. So you can see, like, for example, the robots are able to walk without a problem. They're able to tie a zip tie. This is extremely difficult. Or hold something between their fingers. This is an extremely difficult thing to teach robots to do. And to back up my reasoning that generalist robotics models are going to be the ones that are going to win the challenge, that are going to win in the end, I'm going to draw a lesson from autonomous driving. I was actually working before in autonomous driving at this company, Wave. And back in 2018, when we started, this is what we were able to achieve. So we were using end-to-end learning to teach a car to drive. As you can see, like, it's fairly simplistic, not very impressive. Like, it's just following some road in the countryside. And that's not impressive. That's not the same as the real world, as the city that we observe today. But fast forwarding until last year, Wave was able to show that it can drive in 500 different cities around the world. This was the first time any company was able to do that. So let's talk a bit more about these generalist robotics models and what's special about them. The first question is, how it works. And the answer is you train on a lot of data. So you need millions of hours of data. This is a big, big number. And some of the success stories we've seen over the years, AlphaGo, OpenAI, first they did Dota 2, which is very much less popular than ChatGPT today. And the other example is, again, like Wave, what they were able to achieve in autonomous driving. And now the big question is, okay, how do we get this data? For robotics, one way is teleoperation. So here on the videos you see, basically you have a human who's teleoperating the robot, basically performing a task through the robot embodiment, and we are going to collect the movements of the robot, and we are going to then try to learn from it. The good thing is that this is easy. Like, one famous professor says, teleoperation is the sugar of robotics. But as you know, sugar is not good for you long term. So this turns out to be extremely expensive. It is unable to scale. You require 1 or 2 people per robot, and you're very limited by what you can achieve because you have to develop these different environments where you collect this data. And it's very slow. Like, it's the robot brain that you develop is extremely slow because the human who's performing the task through the robot embodiment is not fast either. What's the other way? Humans. So naturally, there are like many humans in the world. Maybe we can learn something from them. So they perform a lot of tasks in daily. Maybe we can record their movements. So the good thing is that this is fairly easy to collect at large scale. which is what matters, which matters big time. But it's hard to learn directly from it, because there's a difference, there's a gap between the human embodiment and the robot embodiment. And one step towards bridging this gap was developing these devices in white that the human is holding here. They're called UMIs, or Universal Manipulation Interface. So this is basically like the embodiment of where the task is becoming a lot more similar to what the robot sees when we deploy it. And the last way to get data is simulation. So example here, we put a car in a simulator, it starts driving, and we start recording the data. Cool. But the problem is that, first of all, it's large scale, so that's good. But the problem is that it's extremely difficult to reproduce the physics of the real world. We cannot copy and model the physics of the real world in simulation. And second, it's that it's actually impossible to reproduce the structural complexity and the diversity in the real world. So like, when we train something in simulation and try to transfer it in the real world, it cannot work because it hasn't seen what is actually the real world. What it has seen in simulation is completely different. So let's look at the different branches of robotics. And I'm going to connect this in a second. So I've briefly touched about this already. So locomotion. This is first the skill of skill of balancing. So like for a dog or a humanoid, how we can balance. Like we're not figuring out where to walk yet. We're just trying to balance and stay on our legs. Then the second branch is navigation. Now we are looking at the problem, where are we going to walk? Like, we're going to walk safely such that we don't crash into obstacles and we don't cause danger to other people in the environment. So autonomous driving is here an example. And the last branch is manipulation. So this is about how do we manipulate the objects in the real world and how do we interact with them. And I would consider actually locomotion 90% solved today. Navigation is getting close, very, very close. But manipulation is the one which is unsolved. So everyone today is asking, how are we going to solve this problem of manipulation? And that brings me to my third contrarian view, that the solution for one of the branches will not be the same for the others. And let me show you a bit more why. So what worked in locomotion, if we start looking at it, it was simulation, surprisingly actually. What they did, as I mentioned, there is a problem that there is a gap between the simulation and the real world. So the method that they use, they randomize the dynamics in the simulation, and now you actually start seeing randomly the dynamics of the real world during this training by randomizing the properties of the robot, the terrains, and the physics. And you use reinforcement learning as a method to train this. So this is, if I translate this, this is basically a trial and error. So you try something, you see if it works, and you learn from it. And people are able to make this, like, to build these very capable systems using this approach. So like in the video on the right here, you can see how the system even adapts if you injure one of the legs of the robot. So first it might not work, but then, okay, it's able to balance. Similar to how humans work. Here it's locking the wheels of the robot, and instead of sliding, it starts walking, which is a very impressive kind of skill. Moving on to navigation, what worked there? The data was simulation? No. That didn't work at all. What worked was teleoperation. So you have a lot of humans driving through the real world and collecting this data. And the method that worked, okay, we are going to take this data, we're going to copy what these humans do, and we're going to slightly improve by trial and error afterwards. And what it was able to achieve, I already mentioned this, able to drive 500 cities around the world. Manipulation, which is the big question now today. The data, is it going to be teleoperation? Personally, I don't think so. A lot of companies are actually pouring a lot of money today in this teleoperation data, but I don't think that's going to be the way that works. Is it going to be human data? Yes, I strongly think so, because to build humanoids that are working in the environments that we have already built for humans in our homes, we can learn a lot from ourselves as humans. Simulation, are we going to need it? Yes, I'll actually argue that we're going to need it. And this is going to be for these dexterous 5-finger robots. And the methods are going to be very kind of similar to what we saw in the previous branches. And here, yeah, you can see what these methods are able to achieve today. Very different skills with different kind of complexity. I'm going to skip this quickly in the interest of time, and I'm going to go to my last controversial point about hardware. So I would argue that hardware-agnostic solutions will beat the full-stack solutions, which incorporate both hardware and software. And to make my point here, I'm going to, again, take a lesson from autonomous driving. Why I'm talking about this is because a lot of companies today are betting on this. They're building both hardware and software. So the lesson from autonomous driving is that if we take one of the leading companies, Waymo, this is Google's spin-out, they're probably very ahead in the game, and they have only 3,000 cars operating in the world today. They're building both hardware and software. Tesla, another example, building both hardware and software, they have 7 million cars in operation today. In comparison, the cars in the world today are 1.6 billion. So they have barely touched even 1% of the total number of cars in the real world. In comparison, Wave, who are already building only software-based solutions, they are now going to brands such as Mercedes, Stellantis, Nissan. They are making contracts with them, and they can directly put their software on their cars. So the market is operating in a way where the hardware market is already captured. So to scale and to build a solution which actually scales, you need to build only software and go to the people who already have operations in the real world. So finally, my takeaways. Generalist robotics models will be the kings. And once they work, we're going to see a market for vertical applications which are built on top. How we are going to solve manipulation? The big questions today. Human data, in my opinion, together with simulation data. And lastly, hardware-agnostic solutions will rule the market, but we will not be the first one to deploy. Thank you.